How might you put a telescope in orbit that is greater than the rocket that is going to launch it? Is it even possible? Imagining that is straightforward. All that exists in space, or at least in our planetary grouping, is currently there to the degree that we know. Everything in space is extremely old, so the chance of something new and different appearing there seems incredibly improbable. However, the reverse is true. The James Webb Space Telescope, by capturing incredibly accurate photographs of the universe, has caused quite a sensation globally. The magnificence of science lies in its openness to new information rather than dismissing it. Despite the warm reception to new information, some of what the telescope is observing is still frustrating and confusing. What have scientists noted from the James Webb Space Telescope that has left them astounded? What mysteries about the dawn of humanity, as far as we may be concerned, has the telescope unveiled so far? We should find out. Recently, NASA, the European Space Agency, and the Canadian Space Agency collaborated to give astronomers worldwide a remarkable gift and an amazing opportunity to briefly glimpse into the past at the creation of the universe and the edge of time itself. The James Webb Telescope, hailed as the main observatory of the next 10 years, remains one of the greatest scientific achievements in recent memory. It opened this powerful window into creation not as a philosophical speculation, magical time machine, or imaginative depiction, but as a significant instrument. On December 25, 2021, this enormous infrared telescope, more commonly known as Webb, was launched. It was determined to capture photos of the dark and unravel the secrets of our mysterious universe. The state-of-the-art infrared detection equipment on Webb operates on a novel perspective of the universe that Hubble has provided humanity. From its vantage point in low Earth orbit, Hubble has captured numerous, until now never-seen-before images of distant regions and unique epochs of our universe, exploring the history and evolution of galaxies, stars, and clouds. It has described the properties of black holes, exoplanets, and the accelerated expansion of our universe. This groundbreaking work earned the Nobel Prize in Physics in 2011. Webb represents the next stage in our comprehensive understanding of the universe's secrets and the search for life beyond Earth. Hubble's images have defined modern cosmology, opening our eyes to what lies beyond and sparking our existential curiosity. As NASA puts it, if we want to see farther and deeper, Webb can peer back to the beginning of time, while Hubble can go back as far as 500 million years after the Big Bang. How is this possible? The latest space telescope presents several advantages over earlier iterations. The size is the primary astounding aspect. JWST has a 6.5 m mirror, comprised of 18 gold-plated hexagonal segments. This behemoth can collect light from objects many times faster than the 2.4 m central mirror of the Hubble Space Telescope. Since it can gather more than 6 times as much light initially, the significant advantage of JWST lies in its affinity for infrared light. The Space Telescope can detect frequencies between 0.6 to 28.5 micrometers, spanning the mid-infrared to the red end of the visible spectrum. While most of Hubble's sensitivity focuses on visible light, its optics are tailored to capture radiation from 0.9 micrometers in the near-infrared to 2.5 micrometers in the near-infrared. Astronomers can see galaxies that formed less than a billion years after the Big Bang by using the infrared spectrum. These distant objects emit clear and bright light, but due to the expansion of the universe, this radiation is now emitted at longer infrared frequencies. One excellent way of seeing these young systems near Earth is through infrared vision. This also applies to newly formed stars. Young stars are surrounded by dust, which scatters visible light, obscuring our view but allowing infrared energy to pass through. Infrared radiation is invisible to humans, so the colors of images received by JWST differ from what the naked eye would see. To simulate how astronomers often map longer infrared frequencies to the red end of the visible spectrum and shorter frequencies towards the blue, this pattern is adjusted to highlight specific details. JWST serves as a versatile observatory, not limited to focusing on distant celestial systems and star development. Its robust infrared capabilities enable it to observe features in nearby planetesimal belts that traditional telescopes cannot detect. By concentrating on cloud belts on gas and ice giant planets, monitoring cloud formations on Titan, studying Pluto's environment, and probing many smaller asteroids and transneptunian objects throughout the outer solar system, JWST has already achieved several of its initial goals. When NASA's Double Asteroid Redirection Test, DART, spacecraft collided with the asteroid moon Dimorphos, JWST even caught a brief glimpse of the event. This allowed NASA to evaluate the object's potential to alter the trajectory of potentially hazardous asteroids that could intersect Earth's path. Despite the efforts of planetary scientists to uncover the secrets of our solar system, more than 5,000 known exoplanets in our galaxy remain obscure. The vast majority of this additional information lies beyond the limits of Earth-based telescopes, including Hubble. However, JWST has already begun to change. What is happening? While not explicitly intended for exoplanet discovery, JWST detected one around the red dwarf star LHS 47541, located 40 light-years from Earth. This planet's width is only 1% smaller than Earth's, but its orbit around its sun is just 2 days, and it boasts a temperature a few hundred degrees hotter than Earth. JWST's most significant strength lies in its ability to study exoplanet atmospheres by observing transits with significant depth. For its astronomers, this can investigate the chemical composition of these worlds. Most of the compounds crucial to exoplanet scientists are found in the infrared region of the spectrum. JWST's remarkable achievement has enabled the discovery of various compounds on exoplanets, including water, sulfur dioxide, carbon monoxide, sodium, potassium, and carbon dioxide. The gas and dust magnificent incubators known as nebulas are where planets and their host stars form. However, despite their grandeur, these clouds obscure the fundamental processes occurring within them from the rest of the view. JWST's infrared vision has started to unveil these secretive conditions. For example, the Eagle Nebula, famous for its pillars of creation photograph taken by Hubble in 1995, was one of JWST's early targets. While Hubble mostly viewed opaque dust and chilly gas, JWST discovered several stars that had proactively emerged from their natal cocoons. These young stars, visible outside the shadowy blankets of support, are distinguishable by their diffraction spikes in images captured by reflecting telescopes like JWST. These discoveries offer valuable insights into the formation and evolution of celestial bodies, revealing glimpses into the mysteries of our universe. In their objective, stars transform into mature stars. However, JWST has observed much more recently formed objects called protostars. These protostars are still in the process of accreting gas and dust from their surrounding environments. Occasionally, they emit material jets that pierce through their dense surroundings, causing them to emit intense red glows. The two lower supports are among the best examples of this phenomenon. These protostars are estimated to be a few 100,000 years old, according to astronomers. Star formation occurs throughout the universe, and JWST researchers are eager to explore it. Many secrets beyond our world, within our local cluster as well, are yet to be uncovered. Large areas are the Large and Small Magellanic Clouds, the two relatively enormous satellite galaxies of the Milky Way. It is crucial to study these galaxies because they contain about a piece of how much metals are conveyed by massive stars as the Milky Way. This current situation seems to be conditions that won when the universe was only 2 or 3 billion years old, and universes were making stars at a most outrageous rate. The inestimable frameworks outlined during this tremendous early evening time, including those we see right now, were shaped by the impacts during this period. The Tarantula Cloud, situated in the immense Magellanic Cloud, is the closest article in the Magellanic Clouds to reflecting these violent times. The Tarantula Cloud, the most important star-forming zone in the fast universe, makes stars at an irritated rate. About 820,000 stars have been filed by stargazers to date, and the giant stores of hydrogen and helium the cloud holds should be sufficient for a huge number more. The magnificent star cluster R136 near the focal point of the cloud contains different stars measuring somewhere around 100 solar masses. The JWST's initial observations have revealed interesting subtlety of the Tarantula Cloud. In the highlight of the cloud, a sizable air pocket has been gotten out by the remarkable radiation and magnificent breezes of the colossal stars in R136. Undoubtedly, the densest neighbor in regions, which most likely contain youngster stars of their own, can persevere through this assault. The tarantula cloud provides space specialists with a close-by perspective of the conditions they would encounter as they further explore the grandiose late morning impression of adjoining quirks. Often, help specialists see more far-away ones more clearly, as star formation in the Magellanic Cloud reveals insight into similar cycles in the far reaches of the universe. Planets in our nearby planetary group add to the examination of exoplanets. Likewise, research on varying acting universes clearly adds to how we could decipher the nature of the universe's beginnings. JWST was developed to focus on old frameworks shaped toward the beginning of the universe directly, and scientists have been getting a charge out of testing handicap. Bordering areas can routinely go about as analogs for more established, more distant circumstances. A significant field image of the infinite framework SMAC 723 in the Southern Star grouping volumes was perhaps JW's most vital image, moreover, the first made available to the public. This transparency, which took 125 hours rather than weeks for Hubble's different significant fields, gets astronomical frameworks comprehensively. These faraway astronomical frameworks, even fainter and farther away than what Hubble could perceive, are recognizable in SMAC 723. The light we get from this pack is from around 4.6 billion years earlier. However, in view of the pack's giant mass going as a gravitational point of convergence, frameworks seen as further away, including those current within a billion extensive stretches of the huge explosion, are perceptible. The tiniest universes in the field, arranged farthest away, don't seem to be the more made, turning, and curved frameworks closer to our planet. A critical discovery made using the colossal world pack FIT 27144 in structure as a gravitational point of convergence is the view of two universes barely 450 million and 350 million years after the colossal blast, separately. These universes appear remarkably stunning and conceivable, began to form hardly 100 million years after the enormous blast. Researchers are uncertain if these universes contain different weak stars or then again, a couple of extraordinarily splendid people. 3 stars acknowledged to be the first stars in the universe made only out of hydrogen and helium. Another new finding by the James Webb Telescope is the imaging of a social occasion of astronomical frameworks, figuratively speaking 600 million years of age, all along of the universe. While the genuine age may not be particularly intriguing, the circumstances surrounding this disclosure are moderate. By pointing telescopes towards the universe's beginning stages, we can observe events that occurred billions of years earlier when they light over the long haul reaches us. These titanic astronomical frameworks, only 600 million years or less from the earliest beginning point, represent a challenge to our progressing getting it of infinite framework improvement. Their fast turn of events raises issues about the cycles involved and challenges long-held coherent theories. These disclosures highlight the fundamental motivation behind shipping off the James Webb Telescope to stretch the boundaries of our knowledge and challenge recognized legitimate experiences. What more Webb will find stays dark, yet it's certain to continue reshaping how we could decipher the universe through its definite insights and significant capabilities to image. The James Webb Telescope is prepared to uncover more mysteries of the universe and potentially upset our enthusiasm for the universe's introductory ages and universe improvement processes.